This tape has been developed by Tentel to provide valuable information for diagnosis and repair of video cassette recorders. It has been universally recognized that approximately 3 out of 4 VCR problems are a result of mechanical malfunctions. Tentel has developed 4 powerful universal instruments for troubleshooting these VCR mechanical problem areas. Consumer video has undergone an explosive growth, resulting in over 60 million VCRs in the United States alone. These VCRs represent hundreds of different models from dozens of different manufacturers. Millions of these machines have been in use for some time and will soon require servicing. In VCR repair, any one of these brands of VCRs could be the next one to come in for repair. As a result, VCR service and repair was the 8th fastest growing business in the United States in 1988. It would be cost prohibitive to purchase all the various jigs and tools referenced for the hundreds of VCR models currently in use. And for this reason, Tentel has developed universal test equipment to save time and to be more powerful than any of these other methods. In fact, some measurements made with Tentel gauges are impossible to obtain with any other test equipment available anywhere in the world. In this tape, we'll be examining both theory and practice for performing many of the mechanical measurements with Tentel gauges, as well as showing some of the alternate methods where they may apply. Let's look at the mechanical layout for a typical VCR, realizing that there are many variations of these basic components.
Let's look at a typical transport. What we have here is a very simple diagram, but whether it's a top loader where the tape goes down from the top into the supply and the take-up reel, or whether it's the newer front-loading styles where the tape is delivered in this direction, either one of those still are a delivery system to put a cassette onto 2 spindles that are down inside the machine, the supply spindle and the take-up spindle. There were a couple of guides, which I want to go through the tape path in a minute, but a couple of guides back here initially in the rest position, the stop position, that then pull the P2 and the P3 guides that pull the tape out around the video drum so that we can get this 180-degree wrap angle that, of course, it needs. Going through the tape transport, because we'll be using some of these diagrams later in the training tape, from the supply reel, we go through some guides from the cassette itself, go out through another miscellaneous area, depending on the manufacturer guides in this area. Typically, there will be a tension arm out at this point, the tension arm detecting the tension on the tape, feeding that signal back to a brake band that's around the supply reel to try to maintain consistent tension, whether we have a full supply reel or an empty supply reel. We'll be getting into that more later. Other guides leading into the full erase head. This full erase head will erase completely across the tape for video. Coming into an impedance roller. Some of the new machines have eliminated the impedance roller, but most of the machines still have it. Coming into, again, the P2 guide, which we referenced earlier that started here, pulled the tape around the video drum, into the entrance slant guide. This is the final guide before the tape actually goes into the video head. The slant guide sets the geometry of the tape up so that the tape hits this drum so that it's flat across the face of the drum. The drum rotates at the same direction that the tape is coming from. So as we come out of the video drum, we have another slant guide, again, to maintain the geometry of the tape going through the heads. We come into what's called P3, typically the P3 guide. By the way, both P2 and P3 have nested themselves into the V stoppers. There's an entrance V stopper and exit V stopper. We'll show you some of those again in a few minutes, but don't move those V stoppers in general. Those are very critical that they set up the proper geometry for the rest of the machine. Continuing on the tape path, the tape comes down then through possibly some more guides, possibly another impedance roller at the exit, into the audio erase head, and this, of course, just erases the analog audio signal on the edge of the tape. Then we have the analog audio head along with the control track head on the same portion of the tape path. Some more guides again. Sometimes there's some tape shutdown guides, so this again is a variable area in various transports. Coming into the pressure roller or the pinch roller that actually presses against the capstan, which is a rotating component that by controlling the RPM of that capstan, we control the tape speed through the tape, through the transport itself. So the pressure roller and the capstan are what is actually pulling the tape. They're pulling here. They have to pull the tape all around this against the resistance at the supply reel. So past the pressure roller and capstan, there may be another guide or a shut-off circuit connected to a little arm, but then very quickly the tape goes into the cassette back onto the take-up reel. There's various brakes and clutches and so on back in this area, which we'll show you in more detail, and then show you how to measure those as well. But we wanted you to be familiar primarily with P2, P3, the P1 or a guide over in this area, the tension arm, this will prove to be very important. The supply reel, of course, is on this side, the take-up reel on this side, capstan and pinch roller are the basic components in the machine. Just wanted to show you the 4 gauges that we'll be referring to, because as you'll see them next, they'll be coming up singly. We have the tentelometer, the tape tension gauge, most of you are probably familiar with. We have the spindle height gauge, or tush gauge as we call it. This is a new version. This is a 6-function gauge. We have the torque gauge, in this case a TQ600 for various clutches and brake torques in the machine. We have the head protrusion gauge. You can see it here next to the accessory stand, which will show the use of both of these. And also up here you can see the new test cassette for testing the servo performance in the machine. There's a number of checks that the 4 basic gauges that Tentel manufacturers will perform. What we're seeing here is a partial listing of those. The main reason that the gauges have been designed is to prevent the various tape edge damage, tape stretching, crinkling, torque problems, and so on in the machine. But let's just take a look at some of the things that we can do. Hold back tape tension, of course, that's the basic one that was done by the tentelometer years ago. Still the best way in the world to do it because it's the only universal method of measuring hold back tape tension. Tension servo check. This is a performance check of the servo in the machine to see if the servo is maintaining constant tension throughout the reel from one end to the next. Tape tension dynamics, because it's an inline tape tension gauge, you can actually see the dynamics. Customers of ours are telling us that they're finding bad bearings in capstan motors and so on, things that were almost impossible to diagnose otherwise, because it does, of course, the tentelometer does show the dynamics. The video drum exit tension, as you'll see, this is the tension coming out of the scanning video drum. It's important just from a stiction standpoint of whether the video drum is clean, if the other surfaces are operating properly. Next, we get into spindle height for supply and take-up. This is something that you'll see our spindle height gauge will perform. Guide height, also with the spindle height gauge, we'll be able to check a number of guides in the tape transport universally. The elevator latch check, this is a very important function we'll get into very shortly. It shows if the elevator is latching down, holding the cassette properly in the machine. Spindle wobble on the supply, spindle wobble on the take-up have to do with the performance of the actual spindles. We'll again demonstrate those. 4-point flatness has to do with the 4 pins that support the cassette. The end play is up and down of the spindles, both on the supply and the take-up. Number 14, the supply brake stop torque. There's a number of different brakes and clutches in the machine, which again we'll be getting into in detail in a very few minutes. Supply brake stop torque, supply brake drag torque. These are 2 different things. One stops it in one direction, one is more of a restraining force. The stop to play torque, the play to stop torque, these all make sense in a minute. I just want to familiarize you with what we will be doing with these tools. Rewind clutch torque, fast forward clutch torque, take up brake stop torque, take up brake drag torque, take up play torque. And these are all important for tape edge damage and destroying tapes. And I don't know how many of these you're performing currently, but they all are important torques, some more so than others. Take up fast forward clutch torque, take up rewind clutch torque, again very important. Next we get into actually a video head performance level, the video head tip protrusion or wear, which we'll demonstrate. Also we can measure that in microns. Video drum eccentricity, this is important on some of the newer machines, hi-fi machines, some of the older beta machines, if you service those at all. And of course U-matic. The video drum wobble, this would show the alignment of the video drum. It's a fairly new measurement that we've just figured out how to do with the head protrusion gauge. And then just a visual tape path alignment, which you'll see performed also. Let's take a closer look at some typical VCRs, starting from when we first insert a cassette. The TSH V5 spindle height gauge performs 6 functions relating to the various aspects of cassette insertion, cassette orientation, and tape guidance. This gauge replaces all factory master plane jigs, reel table height jigs, post height jigs, and numerous other plates and jigs used for checking the orientation and setup of the cassette, spindles, and guides. We've stripped the transport down so that we can see some of these basic components a little easier. Again, we're going to concentrate on the front end to begin with of the machine, since the first portion of the machine is where the cassette goes in. So if the cassette goes in and it jams or has a tape edge damage problem, then it would preclude all the other things taking place properly. Whether the machine is a top load or a front load, there will be a supply spindle and a take-up spindle mounted pretty rigidly in the machine. As you can see here, it's mounted to the base plate itself. The cassette housing is supported by 4 locating pins, one located here that you can see has a little taper on it, another little taper pin here. These go into holes in the bottom of the cassette, which you can see by looking at a cassette. Then there's 2 other flat locating pins here in the back of the machine. These 4 pins locate the cassette when it's in the machine so that the reels of tape ride on this flat surface on both the supply and the take-up spindle that we can see here. So again, the spindle height gauge goes in the machine like a cassette, locating on those same locating pins. You can see, again, the holes in the front for the front 2 pins, the solids for the back 2 pins. This allows us to measure the spindle height directly on the indicators. These are all pre-calibrated by Tentel. So the ideal location would be zeros on both gauges, which corresponds to 2 millimeters of height of this reference plane, of this spindle surface above the reference plane. 2 millimeters plus or minus 0.2 millimeters is the specification. We can read those by reading zeros plus or minus 0.2 millimeters. Some of the manufacturers, in an effort to eliminate or reduce tape edge damage problems, have actually tightened that spec in now to plus or minus 0.1 millimeters. So you again would be able to just read that directly on these meters. 0.1 millimeters is one of the divisions on the inner scale. 1/1000th of an inch is one of the divisions on the outer scale. So you can read in either English or metric. So we mentioned the reference plane is a 6-function reference plane. So the first thing that we would do is an elevator latch check. If the elevator that carries the cassette into the machine was hanging up or binding, then what would happen is we pushed on the top of the elevator assembly, the indicators would move much like you're seeing here. So as long as this is in fact sitting down flat on these 4 locating pins, then we are reading spindle height above that reference plane. That's 2 of the measurements. The spindles can rotate as we go into fast forward or rewind. You notice we have a light blocking shield here so that we can put the machine in fast forward and rewind. It causes each of these spindles to rotate. If we then see an oscillation on the pointer, that would indicate that the surface that's supporting the reel is not rotating perpendicular with the axis of rotation, or has a lump or bump sort of thing on the plastic surface itself. It would cause the reel in the cassette to sit off and then edge damage again. So we want to be able to put in a fast forward and rewind and not see more than about 1 or 2/1000ths of oscillation when these spindles are moving under the test measuring points. Another test that we can do with the tush gauge is that it comes with a metal block. The metal block has been precisely controlled to a 1/2 an inch wide. As we slide that across the top of the plate, because the plate thickness has been controlled, we can actually detect if those guides are too high or too low, and as we'll show in a diagram, they're adjusted with a little screwdriver across the top. You can actually look in from the side with a mirror that's also provided to see if that guide height is set up properly. So it'd be best to adjust this up or down to match the height of this metal block. P2 or P3, or P2 and P3 I should say, are a little unique in that these actually feed out into the transport, as you can see here, again locking into the V stoppers. So the initial position that we set down here may have to be tweaked up, and for that what you do is once you establish that it's not going to ruin tape from those guides being correct back in this location, put a reference tape in, do the RF envelope measurement, tweaking the heights of P2 and P3 so that you maximize your RF envelope around the video head drum. Here's two typical spindle configurations, either of them doing the same performance in a machine. Both of them, you'll notice, show a washer for changing the height in a machine. So as you add or take out washers here, the surface that supports the reel in the cassette is either raised or lowered depending on the number of washers. You can see the driving splines on this, similar to over here, so this is actually what drives the tape in the machine. This is an example of a typical P2 or P3 guide. Again, if we use our metal block, what we're actually doing is trying to see the height of this guide compared to where the tape should be. See a screwdriver slot in the top. This allows this whole shaft to turn up and down in the locating bar here in the bottom so that we can either raise or lower this guide. Here's examples of tape guides that are either too high or too low, causing tape edge damage. Once the edge is ruined on a tape, you'll lose control track or audio track, so the tape becomes pretty much garbage. You want the tape to ride in the middle of the guide in both cases. So the final view of a guide should be an actual visual to make sure that the tape is riding properly. Even if the height of the guide is correct, you want to make sure that it's straight up and down, that it's square with the tape, and it's not skewing the tape one side or the other. Okay, the 4 points that we described, if those are not in the same plane, we'll notice rocking motion. You can see it there on this indicator. As we try to move it in this direction, we see no rocking. So in this direction, what it indicates is that just like a chair having one leg too long or too short, you get a rocking. The direction that this is rocking now would indicate that this post is either too high or this post is too low. It's easier to make a post lower typically, so we would either Dremel if this was significant beyond about 3 or 4 thousandths of an inch, which is about what it's at, so it's real marginal as far as repairing. But we would Dremel or file or hopefully an adjustment, screw adjustment for adjusting this post slightly lower so that it wouldn't have that rocking problem. The end play of the spindles is fairly important in that as we move the spindles up and down, I'm just pulling up lightly and then letting it go back down, we can see how much end play the spindles have. If there's too much end play, during fast forward and rewind, these spindles can barber pole up and down the shaft that they're on, again causing an erratic tape pack with consequent edge damage. Conversely, if these little washers that are lock rings that are on here, oftentimes just snap rings that push down over the post, if those are too tight, just a couple of thousandths of an inch, then with running, the expansion of the shaft that this is on is less than the expansion of the plastic spindle itself. So the spindle, in trying to turn, binds against the bottom of the little snap ring. So if there's only 1 or 2 thousandths of an inch, just a small amount down here, you can actually get a binding problem in the machine after the machine has been turned on for a while and had a chance to turn enough that it's actually heated through frictional drag of the spindle on the shaft, and actually start to get either a holdback tension problem if it's on this spindle or a take-up tension problem if it's on this spindle. What it would mean if this binds up, the tape starts spewing out, can get wrapped around the pinch roller and capstan, and of course cause a lot of tape damage at that point. You'll notice that on this TSH V5, this little spring-loaded lever off on the right here. It was necessary to add this little lever for the new G chassis VHS machines. The G chassis has a little lever also in the machine at this point that as you're loading the cassette, normally the door, the spring-loaded door, holds that little lever down. So it's necessary to add this to the new models so that it allowed the gauge to fit and to work on these new G chassis machines. It might be worth pointing out that many of these upgrades, what we try to do is design them in such a manner so that some of the old equipment in the field that we've produced before, even before this G chassis was available, can in fact be upgraded. And so just by replacing this side rail with this little lever, one of the older style gauges can actually be used on the new G chassis also. With this lever adapter, the tush gauge loads directly into a G chassis, just like a cassette. It's worth pointing out two additional features of Tentel equipment. Oftentimes we'll try to put the reading right on the gauge itself. This is to aid you. That shows the reading is 0 plus or minus 0.2 millimeters, like we just mentioned, or it shows a specification of 2 plus or minus 0.2 millimeters. So that's on both the take-up and the supply on this gauge. We also supply a master. By inserting the master in the plate, we're able to show that, in this case, of course, it should go to 0, because the master has a 2 millimeter step in the top surface. This 2 millimeter causes the 2 millimeter displacement on the indicator to show up directly. Another variation worth mentioning, some front-loading machines have a switch in the center position so that the cassette energizes that switch when it goes in. Since the spindle height gauge has no solid area, it's necessary to just short out that switch so that you can load it in like a cassette. Once loaded, you can read the indicators directly through the carriage assembly, which saves an awful lot of time. Most manufacturers' method have you pull the carriage assembly out of the machine, which is quite an operation.
You've just seen the TSH V5 spindle height gauge. This VHS format tush gauge should be used for diagnosis of tape edge damage, erratic tape wrap, cassette binding, overall cassette alignment problems, for elevator assemblies with suspected latching problems, or VCRs that have trouble loading the cassette properly. Many of these checks are impossible to do by any other method. This gauge is universal and works on all makes and models of full-size VHS, including camcorders, and replaces all the individual factory post adjustment and alignment plates.
Next, we want to check the motor drive, clutch, idler, and brake performance. These components are probably the major cause of tape damage. Tapes that are ruined with the tape sticking out through the door after the eject mode is complete are usually a result of these components. This is the new TQ600 dial torque gauge. This torque gauge replaces the factory torque gauges 1-to-1. It represents quite a cost savings. The gauge goes on either spindle, has an integral adapter, and reads directly in gram centimeters so that it can be used with any of the service manuals that reference the use of a torque gauge. Some of the advantages of the TQ600 are, first, it's got a larger, easy-to-read dial. The gauge is extremely rugged since it's based on a torsion bar design, which takes a lot of normal abuse. It has a long snout, allowing the gauge to be inserted right through the sheet metal in most of the the newer front-loading VCRs. Also has an integral adapter made from aircraft-quality aluminum, which takes, again, a lot of abuse, so that there's nothing to buy as far as extra adapters. TQ600 comes complete with an 8-page instruction manual that shows 11 different torques in the VCR. The gauge also comes with a modified teach cassette that allows you to put the modified cassette into the machine to have the machine go into the various run modes. With the machine in the stop mode, by placing the torque gauge on the supply spindle, we'll get one reading, and this is for a typical machine again. Look in the service manuals if it varies much from these readings. In the counterclockwise direction, it should read approximately 50 to 150 gram centimeters. You can see this is reading about 125. In the clockwise direction, it should be fairly high torque. As you can see, this one is actually going over the 600 gram centimeters, so that shows that the brake is in very good shape. On the take-up spindle, it's just the opposite. In the counterclockwise direction, it should be a high torque reading. You again see it going up to almost 600 gram centimeters before it starts slipping. The clockwise direction, again, it's about 125 to 130 gram centimeters. both of these readings would fall on the chart. Machine in the play mode can measure our take-up torque and at what point it's slipping. Going from play to the stop mode causes a restoring torque on the supply reel to pull the tape back in. On the supply reel, in the rewind mode, there should be plenty of torque to make sure that the tape gets pulled. You can see the torque gauge is definitely going over 600 gram centimeters on this machine. In the take-up spindle in the fast-forward mode, same reasoning applies. There should be lots of torque to drive the tape forward. And you can see that its brake is very good, or the clutch is very good on this machine. The TQ600 can be used on all types of machines, including the older top loaders. If the new front loader doesn't have cutouts in the elevator or carriage assembly, it will be necessary to remove the assembly per the instructions for that particular machine. The TQ600 can be field checked for calibration since it's based on a torsion bar. As long as the gauge moves freely and returns to zero, there's virtually nothing else that can go wrong with the gauge. The accuracy is determined by the torsion bar that's in the gauge that is comprised of its length and its diameter and its material, which can't change in the field. Check the pinch roller to make sure that it rotates freely, and for any signs of wear, glazing, or abuse. Replace it if it looks like it is going to cause a problem. Check any of the rotating guides in the machine prior to insertion of tape, such as the P1, P2, P3, or any of the guides that are supposed to roll with the tape in the machine. Rotating guides that hang up will cause tension problems later. Now that we've checked the machine for holding the cassette properly with the TSH V5 and for proper tape movement and braking with the TQ600, we can feel confident in inserting a cassette.
In addition to the checks previously made with the spindle height gauge for finding sources of cassette binding, tape edge damage, and tape destruction problems, we've now performed 11 torque checks with the TQ600 dial torque gauge. The dial torque gauge will analyze the performance of the various brakes, belts, clutches, and idler assemblies that comprise the transport system. More specifically, use the torque gauge for diagnosing tape stretching and destruction problems, for ejected cassettes which have the tape sticking out the door, for erratic tape movement while in the play mode, for poor fast-forward and rewind performance, and for discovering marginal torque or tape handling problems which could result in a nagging service callback. The integral universal adapter works on all VHS brands and models. The TQ600 is accurate and provides readings directly in gram centimeters, as specified in factory service manuals, and readings are interchangeable with factory torque gauges. The TQ600 is actually easier to use than older style torque gauges and is more universal due to its unique design. With the cassette inserted, the main function that we haven't already tested for is visual tape guide alignment. You can see here pin post P1, P2, P3. There may be another guide over at P4. Check for edge damage or curling along any of these guides. The Tentel T2H7UM 10-kilometer tape tension gauge is the only universal method of measuring holdback tape tension. The reason the tentelometer is so universal is that it allows us to measure the tension near the inlet to the video drum, which is where the standards are provided. SMPTE and the Japanese standards provide a reading right here at the inlet location of 0.3 to 0.45 newtons. Translating that Newton measurement for the drag of the final entrance slant guide and the rotating P2 guide provides us with a
proper tension reading of 23 to 35 grams between what would normally be an impedance roller over here. You see this model has an impedance roller a little further back. So we'd want to measure the tension just prior to the final P2 entrance guide. Some of you may be familiar with this device. This is a tension cassette. Be aware that the tension cassette is not a universal tool, since it operates by measuring tension or torque inside the cassette itself. As different machine models and brands have different tape path configurations on their way to the video head, the standard specifies 0.3 to 0.45 newtons. By the way, there's about 102 grams in 1 newton. So with the tentelometer, we're able to measure the tension at this point, which is a consistent point in all brands and models of machines, since there's just the rotating P2 and the final non-rotating slant guide. But again, with the tension cassette, as the tape path varies on its way, it'll require different torques or tensions down in the cassette to assure the proper tension at the inlet location. Here's a typical VHS tension servo arrangement with a tension arm out in the tape path connected to an arm with a spring. This arm is acted on by, or this post is acted on by the tension to either relax or tighten this brake band around the supply reel. As the tape goes around one guide, around this tension arm, and then another guide, the higher the tension is, the more force it applies to this arm to relax this brake band around the supply reel. Here's another configuration showing the rest position for this tension arm. As the cassette is inserted, the tension arm pulls out in contact with the tape, supplying the proper amount of torque by this little brake band that goes around the supply reel itself to provide the right amount of tape tension. Here's a slightly different but similar arrangement for the holdback tension arm. Notice the tape guides can be different locations and different positions, but basically the arm from the supply reel does come out with a post out in the tape path, so that as the higher tension moves this arm back, it slacks this brake band that's around the supply reel. Here again is another similar arrangement, but here they've eliminated the first post going out of the cassette. They're using the cassette post itself coming out to the tension arm and then around P1 post. So this is a little different than the other ones in that they've eliminated a post at this location. Here's an example of a brake band as it goes around the supply reel. The fixed end of the brake band is adjustable. I've loosened this screw so that I can show the adjustment here. Providing more holdback tension, you would tighten the band. Less holdback tension, you would loosen the band. This arm, the tension arm, is then connected to the other end of the band, so it does the same thing, being acted upon by the tape. You want to make sure that the tension stays in the 23 to 35 gram range by moving the fixed end to keep it within that range. If it turns out it's impossible to get the tension in that range, say that it goes from 20 to 50 grams, it may be necessary to change the position of this spring or actually replace the little brake band. Another advantage of the tentelometer is the calibration can actually be checked in the field with the 1 ounce weight and VHS tape shipped with the gauge. By moving the tape in the same direction as the tape will go in the machine, you can actually take into account the effect of the drag on the non-rotating guide pins on the tentelometer. The 1 ounce weight simulates a holdback tension in a typical VHS machine. Inserting the tentelometer near the inlet impedance roller allows us to measure that tension very easily. The standard again is 23 to 35 grams. Because of the operation of the servo, we found it's best on a full T120 cassette if the tension is in the 23 to 27 gram range. Note I'm pulling the impedance roller back by hand so that I can insert the tentelometer at that point. The tentelometer works on all brands and models of VCRs. Measuring tension on the new G chassis is very easy once the printed circuit board is moved out of the way. The two outer probes on the tentelometer are slightly longer than the center probe, which allows you to actually rest the gauge right on the bottom of the deck. On some machines, by moving the inlet impedance roller, it causes the servo tension arm to actually move, changing the tension. On these few machines, leave the inlet impedance roller in its position, but rather rotate the tentelometer 180 degrees, using the inlet impedance roller as a guide for placing the probes of the gauge down over the tape. Let's just quickly review the mathematics involved in converting from the standard of 0.3 to 0.45 newtons at the inlet location. By the way, again, 1 newton equals 102 grams, or very close to it, so that mathematically we can derive this tension range of 23 to 35 grams with the tentelometer at this point. The tentelometer will measure this tension going into the P2, which is a rotating guide. So we have the tension coming in versus the tension coming out. Because this is a rotating guide, these tensions will be virtually identical. However, on the slant guide, a non-rotating surface, the tension coming in is related to the tension coming out, and it's determined by the friction of the tape against this slant guide and the wrap angle around it. They're related by the formula, the tension coming out divided by the tension going in for this non-rotating guide is related by E, which is a natural number of 2.72, raised to the mu theta power, where mu is a coefficient of friction of the tape against the slant guide, and theta is a wrap angle, which for most machines is about 45 degrees. That would be expressed in radians for this computation. We thought a brief review of the terms torque and tension would be useful, since some of the factory service manuals seem to use these terms interchangeably. As we'll show, they really aren't interchangeable terms. Torque, when it's related to a round reel like we're using in a tape path, torque equals the tension exerted on that tape path by the tape times the radius, which is half the diameter, times the radius of that particular reel. So if we use an actual instance of a T120, if we measure across the T120, we can see that we have an 8.5 centimeter diameter across the entire reel. This diameter, when divided by 2, gives us the radius of 4.2 centimeters. If we have an ideal tension of 30 grams on that reel, 30 times 4.2 provides us with 126 gram centimeters for this particular full reel. If this torque were applied to a machine and we didn't have a tension servo arm, we can demonstrate that by measuring the small reel and seeing that that measures 2.5 centimeters diameter, the 2.5 centimeters diameter provides a 1.2 centimeter, half of this, radius. Dividing that radius into the torque that it took to get the correct tension here provides 105 grams of tension on the tape out at this point, which would, of course, be very destructive. So this shows once again that 3-to-1 ratio. The 4.2 centimeters here divided by the 1.2 centimeters here provides the 3.4, or over 3-to-1 ratio of the changing tension from one end of the reel to the other end. So that tension servo is very important in the machine. Tentel's provided a new test cassette, short for Tension Evaluation Servo Test, to actually check the entire tension servo system of the machine. By inserting the tape into the machine, as you would a cassette, pressing play, each revolution of the supply reel exercises the holdback tension arm throughout its entire range of working. By measuring the tension with the cassette, we want the tension to stay within the 23 to 35 gram standard. Here's another configuration showing some of the maneuvers the various manufacturers go through to position one end of the tension post in the tape path. Some are measured from a plate. These are all unnecessary when using the Tentel test cassette, since what you do is put the screw in the center of the slot on this end of the fixed end of the brake band, which goes around the supply rail. Make sure or test with a test cassette to see if the tension is staying in the 23 to 35 gram range. If it's high, you would relax this or move this out. If it's low, you would tighten it up, moving back and forth in this direction on the fixed end.
When using a back tension cassette, extreme care should be exercised to make certain that each cassette is used only on those transports that they were designed to be used on. This section has shown why these tension cassettes are not and cannot be designed as a universal back tension measuring device. The T2H7UM 10-ohm tape tension gauge has been shown to be the only universal method for measuring holdback tape tension, and its accuracy can easily be verified in the field. The dynamic measuring ability of the tentelometer also allows the entire tension servo system to be easily measured. Low tape tension can result in intermittent video signal, increased video dropouts, intermittent control track and subsequent intermittent picture breakup, skewing errors with video hooking, tape guidance problems and subsequent tape edge damage, intermittent audio, and other causes of tape destruction. High tape tension can cause skewing errors with video hooking, premature video head tip wear, tape edge damage due to high tape tension at guides, and tape destruction due to stretching at high stall tensions. The tentelometer can quickly and easily be used to measure tape tension at points along the tape path, particularly near the video drum inlet where universal tension specifications are provided. Use of the accessory test cassette will assure that tape tension is maintained within the specified operating range throughout the entire length of a T120 cassette.
Tentel's fourth product is a video head tip protrusion and drum eccentricity gauge. This gauge allows an accurate, safe measurement of the fragile video head tip. The gauge reads directly in microns, so you can see where the heads are along their wear cycle. Why is this important? Well, if an older or low-end VCR comes in for repair with an apparent expensive defect, measuring head life will allow an intelligent decision to be made on the practicality of repair. Conversely, if significant life can be shown, rather than guessing about a 4 or 5 year old machine, the customer is more likely to authorize a repair charge. Let's look at what comprises video head tips. Here's the underneath side of a video head drum removed from a VHS recorder. In this picture you can see the video head tip connected to this brass piece of metal held on to the aluminum drum by the little mounting screw. That head tip protrudes out into the tape path. For a new drum, we're looking at about 45 plus or minus 5 microns. For a worn head, we're looking at about 5 to 10 microns. Some technicians think that they can actually look at a video head tip to see how worn it is. I think it might be worth looking at some of the units that we're dealing with. 1/1000th of an inch represents 25.4 microns. So that means that each thousandth has 25.4 microns, or you'd have to divide 1,000th into 25 pieces for each of those microns. A new head protrusion reading would be about 45 microns, or about 1.7 thousandths, or a little less than 2/1000ths of an inch. To give you an idea of the size of this, if you take a dollar bill out of your pocket, take a micrometer, you'd see that it's about 5/1000ths of an inch thick, which represents about 127 microns. Again, a new video head falls in the range of 40 to 50 microns. One that's worn out falls between 5 and 10 microns. So what we're looking for is the difference between a 40 micron reading and a 10 micron reading, the difference between a new and a machine that has many thousand hours on it. So as you can see, it'd be virtually impossible to see what the actual wear visually is on a video head tip. Other common methods for video head evaluation include the head checker and the signal substitution method. It might be pointed out that both of these methods, at their best, show whether or not the head works or doesn't work, but they don't really give much information on how good or how bad they are, other than the fact that they work or don't work. The head protrusion gauge from Tentel shows you exactly where you are along this critical wear cycle. Here we'd like to introduce you to the parts that come with the HPG1 and the accessory S1 stand that we recommend for the VHS machines. What I've done is just taken the parts from the S1 stand out of the box that it comes in just to save some time. The stand has a very tight pivot in the back, allowing the stand to be set up so that the machine will actually go on the legs of this stand. We'll notice that the stand locates on three points, so it'll sit virtually on any surface. The post that comes with the stand screws into a tapped hole in the back. It's quite important that we have this post tight. And to tighten it, let me show you what we do. Screw it in by hand until it's snug. We then take the horizontal arm and slide that down over the post using the 1/8 inch pin that's provided for tightening the horizontal arm onto the post. Just use that then as a wrench to actually tighten the post into the stand so that there's no play at this point. Since we'll be measuring later microns of head protrusion out off the end of this arm, it's very important that this stand not wiggle or be loose. Once that's tight, once the post is tight, loosen this arm and slide it out of the way. We'd now be ready to set a VCR on the stand to set the head protrusion gauge into the horizontal arm. Okay, now we have the S1 stand assembled. Let's take a look at the parts that come with the HPG1. First of all, there's the little indicator itself. This is the heart of the device. The indicator, you'll note, is calibrated in both microns and 10,000ths of an inch for that very accurate reading to show where we are along the wear cycle. The other end of the indicator has a little self-aligning plastic foot that actually rides on the drum. You'll note later that the head tip is aligned with the center of the E. The E is what allows us to actually do the measuring, where the top of the E rides on the upper drum, the bottom of the E will ride on the lower drum, and the center of the E will actually do the measuring of the little video head tip. We'll show that in more detail in a minute. Second in the kit, we have what we call the XY slide. This is the provision for actually positioning the indicator against the drum. The XY slide consists of a coarse horizontal adjusting method, similar sort of thing for vertical. There's a knob here to adjust the vertical position. What we'll want to do is position the center of that E, as I explained, onto the video drum aligned with the video head tip. There's a little dovetail in the side of the, or in the back of the indicator. It just slides into the dovetail mount on the XY slide. Should be pointed out at this time that each of these knobs is actually spring-loaded. We did that on purpose so that we would have a provision that the gauge wouldn't drop into the machine accidentally unless you push the button. And of course you can see that would not be a good situation to drop in accidentally. So when you're adjusting it, just push the button and then you can actually do the coarse adjustment this way. But when you let go, there's enough force to actually hold the indicator from moving. Once the coarse adjustments have been made, there are micrometer adjustments for both the horizontal as well as the vertical to do the final positioning of the tip against the little drum. Some other parts that come with the HPG1, quite frankly, you won't even be using with the stand. This is a universal clamp. This provides a way of adapting the clamp to some portion of the sheet metal on typically an industrial video recorder. At that point, once that's mounted on the sheet metal, the HPG1, the 1/4 inch pin in this, mounts into that portion to form a rigid mounting point. At this point, what we'll be doing is putting it onto the stand in the 1/4 inch hole provided on that. So if you can imagine, and we'll put one out here in a very short order, of actual video drum sitting on the stand, or video machine sitting on the stand with the drum, of course, positioned near this head. Another part in the kit that, again, you probably won't be using is an extension block. The extension block is used to get more height from the stand, or from the universal clamp. So again, this 1/4 inch pin would go into the top of this, but we probably won't be using either one of these. Also in the kit is a little L bracket. The L bracket has a small hole. The idea of this was to actually remove a screw from a machine that wasn't made rigid enough to mount the universal clamp to, or didn't have a suitable point for that. Tighten the screw in the hole, and this gave us a vertical surface that we could in fact put the universal clamp on. Again, with the stand, you won't need this. Also in the HPG1, you get a little flashlight to help do the alignment, and a little alignment mirror to actually be able to sight down a sighting groove that we'll point out to you in the machine to actually perform the adjustment. And then all of these are explained in the booklet that comes with the machine. Entire setup procedure and parts positioning and so on is explained in this booklet. Okay, this is a close-up of the HPG-1 foot. You notice that the whole shoe assembly, the aluminum portion, is actually mounted on a slip clutch. The reason for this is that we want this little shoe, the black plastic part, to actually be self-aligned to the drum surface. However, it can only self-align to about ±5 degrees. What that means is that we want to make the back edge of this aluminum shoe visually parallel with the drum. We don't want the drum sitting over here at an angle like that if the shoe is like the angle shown. So as we would move this over so that it would be visually parallel to that, the little black foot then makes up the difference for the alignment. Don't be afraid to move this. It's been designed so that this is in fact on a slip clutch, and most gauges, indicators, are shipped to you at a 90-degree position so that you have to realize immediately that this is on a slip clutch and has to be moved down in this position for use. Okay, what we'd like to do is first go through the sequence of operations for setup using this stripped down chassis, and later we'll show one, but it's a little harder to get the camera in when the complete machine is there. The horizontal arm on the stand, as we mentioned before, this is basically loose now. What we want to do is keep this about 2 or 3 inches above the video drum and about 4 inches from it in this direction. That's for the ideal location. Basically what the horizontal arm is setting up is this locating hole right here, so we can come over with the rest of the mechanism to the head. As far as what direction on the head, why did I choose to put the arm on this side as opposed to this side? We want there to be the same diameter on the upper and lower drum. The lower drum has I think they call it a babbitt, formed into it, where there's actually a ledge right here that the tape rides on. So we want to make sure we get in some portion of the drum area that has this similar upper and lower diameter. Once we have the arm in place, we want to slide the indicator onto the dovetail and lock it with the dovetail nut. So just tighten this down. You'll notice again that if this was brand new out of the box, this may be in the 90-degree position. Just get that down visually straight. Once it's straight, we know that we're close to where it will be in the machine. Both of these knobs, leave those loose because again, with that spring load, we don't have to worry about those falling into the machine. At this point, we want to bring this horizontal arm basically towards the center of the drum, because we're going to later use the horizontal micrometer adjustment on the end of the arm out here actually to do the final positioning of the tip against the drum, engaging the pointer with the drum. As we mount this to the machine, make sure the little tip down below doesn't hit any guides or anything, and then just move it over so that we're close, both horizontally and vertically, before we lock anything down. You can notice also that it's possible to tilt this to get the tip visually perpendicular to the drum. This is what is shown in the manual, if you have the manual, on page 8, figure 9. That's the tilting of it. So with everything really pretty loose at this point, you get it over close. Now it's time to start tightening the knobs. So we tighten the knob on the horizontal arm. We tighten the other knob. And by the way, the knobs that have the 1/8-inch diameter holes in them should be really snug with the 1/8-inch pin that's provided. Also, I've located the head tips out of the direction while I'm doing the initial setup. This is to prevent any accidental crashing, if you will, of this against of our tip against the little drum. We want to make sure that we're working, very safe and not going to hurt anything. Once we get this positioned as close as it is now, make sure you just by hand snug these 2 knobs down. What this does is it makes it so that this is tight except for the adjustment knobs. So as we sight down the sighting groove, we actually will see the head tip at the end of the sighting groove. Right now, with the expositioner, I'm going to come over without the head against it. The head is back away. Bring this over and actually do an alignment until the pointer moves. You see the pointer moving there. And then back it away about a half a turn. This provides up and down motion. We don't want to do up and down motion with this tip against a head drum, or with a head tip. Okay, what I'm doing now is just moving this down and sighting down in the mirror. We'll set up the camera so that you can see what I'm seeing here in a minute, so that the little groove is actually aimed at the head tip itself. Once that's accomplished, the vertical alignment is complete. We use the horizontal micrometer adjustment to actually engage the tip with the drum, moving the pointer from what's called the rest zone, which is where the pointer rests when it's not touching anything, up to the preload zone. You'll notice that, again, our discussion of microns, 25 microns in 1/1000th of an inch. It doesn't take much motion here to give quite a bit of motion on the indicator. So once we're set up, don't lean on the machine because the metal will flex enough that that will change things, but just rotate the head tip through and subtract the base dimension, the starting dimension, somewhere in the preload zone. It could be anywhere from 0 to 30 or so microns. We'll subtract that number from the upper number. So right now I'm at about 3 microns with a head tip under it. This one only goes up to about 13 microns. So it shows that these heads are in fact worn. We only have about 10 microns of protrusion. Okay, we've shown the setup of the head protrusion gauge on the bare chassis. Let's pick one of the tighter chassis, and this is a newer chassis. This again is a G chassis. Just for tape tension also, we had to move the board out of the way. This position also allows access for the head protrusion gauge. So we mentioned before we want to bring the horizontal adjustment arm in about 4 inches or so from the drum, and then in this case right down towards the top of the printed circuit board. It's very important on machines like this where there's printed circuit boards in the top to, of course, unplug the machine. Shorting out one of these is going to create a new set of problems for you, so let's work safely. I've already gone ahead and mounted the dovetail to the dovetail mount on the indicator, and as you can see it's located at the top because I know already that I'm going to need a fair amount of reach to get down in this machine. So I've loosened the horizontal course adjustment and the vertical course adjustment knobs to allow me to actually place this into the horizontal arm and then position in a course adjustment the gauge over, the indicator over to the actual video drum. Okay, I'm aiming, this is fairly important, I'm aiming the horizontal arm basically at the center of the drum as close as I can and still getting around the printed circuit board. So I'm going to be using the horizontal adjustment here to actually engage the tip against the drum later. So it's important that this not be too much at a right angle like that, or you won't be able to use the horizontal adjustment of this to actually engage the tip against the drum. So try to keep that assembly as straight as you can. Again, can lean this so that the tip stays fairly perpendicular to the drum. Once you get it close, and it looks like we're there now, tighten the other knob that requires the 1/8 inch adjusting pin so that too is snug. Check this one, it's snug. The horizontal adjustment knob should be tightened now that we're down close, and the vertical knob can be tightened. I'm rotating any head tips out of the way so that as I come in I don't want to cause an accident. I'm using the micrometer adjustment to engage the tip against the drum
At this point, it's a good idea to look down in and see if the tip is in fact perpendicular to the drum. If it's not, do kind of a tweaking operation with this so that the tip is in fact perpendicular to the drum at the tip area there. Once the tip touches the drum, draw it back to the rest zone and then back another third of a turn or so on this. And that'll give you about a 32nd of an inch of play so that you don't take any chances on touching the video head tips and harming those, because they are fairly fragile. At that point, we want to sight down the groove on the side of the foot and actually aim the groove at the video head tip, performing this with the micrometer vertical adjustment knob. Once the vertical alignment is done, make sure the vertical course locking knob is tight, the horizontal locking knob is tight. Engage the horizontal micrometer adjustment, moving the pointer from the rest zone up somewhere in the preload zone. I personally like to get around 10 microns because we're going to be subtracting this number after we have the head under the probe, so it makes a number nice to work with. So it's about 15 microns. So I rotate the head tips around. I'm going to subtract that 15 from the number when the head tip is under it, which is about 62 microns. So it shows 47 microns of head protrusion. Bring the second tip around, 12 micron base, subtracted from about 61. So again, it shows about 48, 49 microns of head protrusion. So this is, in fact, virtually a brand new machine. The tip, it should be pointed out, is very safe for head tips since the little plastic foot has a very low amount of force and radius corners. You can do things like this that are not very smart to do, but it actually is an order of magnitude as far as not harming the video head tips. Perform the eccentricity measurement, which is critical on the VHS Hi-Fi and some of the older Beta and Pneumatic machines. Simply position the tip so that it's on the upper drum only. Engage the pointer, moving it from the rest zone. It's not quite as critical that it be up in the preload zone, but it's still a good idea to work up in there. And then very lightly turn the drum smoothly, noting any deviation in microns of the drum surface. If the drum is off center, would indicate, I'm not sure how to simulate it, but the pointer would oscillate back and forth as you move the drum around. To correct those problems, different manufacturers have different ways, but basically what you need to do is take the part that reads the highest and position that under the foot, loosen the screws, move it over half that distance, and it's a lot harder than it sounds, believe me. Move it over half that distance when you retighten the screws. Check it again to make sure that it runs true.
Although it may be beneficial to use the head inductance measurement, signal substitution, or resistance measurement to confirm the electrical integrity of video heads, none of these methods provide an indication of the useful amount of remaining head life. In contrast, by measuring head protrusion with a mechanical head protrusion gauge, providing readings in microns, an accurate evaluation of exactly how good or how bad video head tips are can easily be made. The Tentel HPG video head protrusion and eccentricity gauge quickly provides service justification based upon the remaining video head life. Many VCRs are worth repairing, only if it can be shown that significant head wear remains, and customers are often looking for this increased confidence factor as to why they should have repairs done. The HPG-1 provides that confidence factor. When performing estimates, the HPG-1 often allows you to substantiate the cost-effectiveness of repair, even on non-operating units. The HPG-1 will also verify the drum eccentricity, critical for diagnosing audio wow and flutter on VHS Hi-Fi machines, and allows the quality of protrusion and eccentricity to be monitored during head drum replacement. The HPG-1 is universal and will work on all VHS, beta, and pneumatic VCRs.
The dynamics of these 4 gauges would be if a machine was questionable as to whether or not repair was justified, first check it with a head protrusion gauge to see if the machine is going to be worth repairing. Next, check the machine with the spindle height gauge to make sure that there's no edge damage problems or cassette binding problems in the machine. Next, the use of the torque gauge will show various torque problems caused by clutches, brakes, and motors in the machine that would cause tape destruction. And of course, the tentelometer is still the best way for measuring the whole back tape tension to prevent hooking and flagging and tape destruction problems in the machine. We hope this tape has been able to communicate the power, the universalness, and the time-saving ability of these 4 gauges. We guarantee your satisfaction. Tentel offers these gauges factory direct in the United States, so please feel free to contact us for additional information regarding the use of these gauges or for ordering information. Our toll-free number is 1-800-538-6894.